then they have the video. It's actually quite nice. And it's really
afternoon session. I'm happy to introduce Matthew Evans. Lucy Lorraine is a research fellow there. He is an expert in high throughput workflows for materials discovery and design, with a focus on finding new materials for rechargeable batteries. Okay. Yeah, please. Thank you very much.
Yeah, so thank you all. Thank you to the organisers, of course, for inviting, well, I think inviting someone at least to speak about OPTIMADE. I don't know if you actually asked for me specifically, probably didn't, but here I am. So I guess this is going to be a bit of a different session to the other one we've had so far, in that I'm going to basically avoid talking about machine learning at all. So, you know, if you want to leave now, I think the door is still open, but I hopefully will at least convince you of some of the practicality and usefulness of something we've been developing as a consortium called the Open Databases Integration for Materials Design Consortium, or OPTIMADE. So you've all been filling out this this poll to start with. Hopefully everyone's done that now, and I think I'm not sure how much the results balanced out, just because I tried to make you feel bad, but at least the first two people were a very biased sample who hate databases, apparently, but yeah, that's fine. But clearly there's a universality in a lot of the work we do, that we need crystal structures, or we need some atomistic model as inputs to our, whether they're sort of DFT codes, electronic structure codes, machine learning, algorithms, whatever. We often have to start from somewhere, and that isn't always scratch. So it's good to see that it's not going to be too hard to sell, hopefully, on the importance of crystal structure databases. It's the second slide. Okay, so I forgot that I put Tim Pookie in there. That was sort of testing the GIF functionality. So he plays for my local football team, basically, in the UK. So I thought I'd bring him in as a link between here in Finland, or there in Finland. But I see people haven't filled out this question yet, so maybe if I just give you 30 seconds to read it. We're basically asking how people currently interact with the databases that they use. Sort of out of the people that answered yes, I guess, on the first question. And so we'll run through the options while you're looking. So many databases these days have sort of nice, fancy web UIs, which, you know, if you have a student that's good at web design and wants to waste their time on it, then you know, these things can be fantastic for getting new users. Many of them have REST APIs, which, if you don't know what that is, we're going to cover. If you do know what it is and you've used one, then please say yes to that part. Many also have sort of language-specific APIs, so something like the Python API, where you interact directly in code. Sorry.
Should we answer this question?
Yes.
If I use this code, I get to a different question. I don't know if it's the same for all of you.
I think you need 2%. Yeah. Yes.
There we go. Okay. Sorry about that. So now he's even bigger and even more fierce. But yeah. So hopefully we should now be able to answer this question. Thanks for pointing that out. And then yes, the other options would be just having sort of a static data set. So maybe the database you work with is sufficiently small that you just download it all and you filter it locally, and maybe that's the most performant thing for you. And then maybe you're one of the probably 2 people in the room who have already used an OPTIMADE API, in which case you should select that. So I don't want to dwell on this too long. We're getting some fairly good statistics already. There's one, thank you. So primarily it's interesting people using language-specific APIs. So I guess mostly we're looking at Python here, which is what the example is going to be. But yeah, I'd like to sort of interpret this idea of a database quite broadly to also mean like on disk, anything that sort of could be represented as a spreadsheet, I guess you could call a database. Because the idea is with what we're going to talk about, the OPTIMADE API, so you're going to expose that data to potentially a broader audience, and also with some sort of functionality filtering it, as we see. Okay, cool. That's, I think, useful context for me at least going forward. So to start with the presentation proper. Yeah, so I thought it was only right to use a very nice example of a paper from Alto, so from Patrick Troop, which is this last review on data-driven material science. So this is a lovely map of pretty much every materials-related database that I can think of as well, that was summarized in this review paper, with a nice timeline going back to 1965. I hope you can read this small font. So, right at the start there, we have the CSD, the Cambridge Structural Database, and the CalFAD, which are both sort of still going. I think mostly they're probably still going. Is used in our vague field, I guess the ITSD is used very frequently in organics. And then you start seeing through the early noughties, theoretical databases. So being able to actually compute properties of materials with things like DFT in a robust way so you can actually populate a database. So you can see A-Flow, for example, in 2003, Materials Project in 2006, and various other names you recognize. And the way this has kind of been termed, I guess, in the field, in the literature, is that this is a sort of a new paradigm almost to doing this kind of structural science, where you're driven not just by these icons on the left, so I think that's sort of simulation, somehow sort of trial and error, and this kind of discovery, but also collating data sort of globally into databases that provide new insights sort of on aggregate, that just individual results wouldn't on their own.
Oh, that's experiment theory and computation.
Oh, thank you very much. That would make a lot of sense.
Second and third paradigms, yes.
And I put a painfully slow slide animation there just to emphasize that the OPTIMADE logo suspiciously fits exactly within that new materials section. So very, very ominous. So what actually is OPTIMADE? Well, I guess there's a really boring answer, which is the one I'm going to give, which is the one on the website. So we are a consortium that aims to make materials databases interoperable or interoperation by developing a common REST API. But really, so OPTIMADE is just, it was just a collection of people who got together to think about this sort of similar problems. So it started in 2016, and I bring this up because by design it started very wide. So it had representatives from pretty much all the major databases, at least in theory, at that time. Many of the ones I've just sort of listed in the last slide. And we've had these annual workshops basically ever since. So I personally got involved in 2018 when I was a PhD student, along with over 60 people now have sort of been involved. But the core of it is really just it's a text document. It's 25,701 words, or it was like last night. Maybe it's been changed since then. And this is just a loose contract between people who make this consortium to do the things we said we were going to do. So to serve data in such a way that we become interoperable. And that's really the core of it. It's sort of important to remember that it is really just a set of words. It's nothing particularly official. It's not a grant that's joined between all these people. It's just sort of a very loose collection of now up to 19 different registered providers. So you could think of those as distinct research groups or distinct funding sources, I guess. And it gives you access to 26 million crystal structures. Again, press the wrong one there. Again, as of last night, at least, this is the sort of automatically generated dashboard to make sure I'm not making up these numbers, although this is a screenshot of it. I could have got the latest, but there are 19 providers. There are 22 databases from those providers, and I insert some commas there. Does that look like 26 million? It doesn't, but I know the answer is 26 million, so something's happened there. But essentially, we have a huge amount of crystal structure data between these providers. So why did we come up with it? Why do we need OPTIMADE? why couldn't we just keep going? And maybe we don't need optimization, maybe we could just keep going, but why did we decide to try at least? Well, purely on sort of a pragmatic point of view or practical point of view, getting access to this data is across these different databases. If you want to do any kind of sort of unification of data sets or any kind of filtering that isn't restricted to one database, then you run into all these issues where, of course, everyone has their own format, everyone has their own different syntax way of structuring the data online, on the URL formats, things like this. So that would be sort of syntactically different. They also vary in the sort of actual sort of scientific taxonomy they use. So they may all have the same concepts within them, but they use different names for those concepts. So you have a lot of sort of mental work to map these things together, and they can't really be done automatically at all. And they also vary in what I've called here semantics. So, what does it mean for something to be in this database? A crystal structure is just some periodic, or maybe not even periodic, it could just be structure, arrangement of atoms, and its presence in the database sort of has some nebulous meaning attached to it. And you kind of have to know the database to sort of tease that information out. And I don't claim we solved that part, but hopefully the first two at least I can talk about. So each database as well has its own niche, whether it's a particular experimental technique that it sort of applies to lots of materials, or a theoretical technique, of course. So to pick a few examples. So people are probably familiar with materials projects. And the materials project approach to take essentially every reporting crystal structure, run it through a hyperconverged GHG workflow. So you can do things like phase stability, sort of global phase stability, so we have all these calculations. But then also over the years, an increasing number of properties that you can get from DFT and other methods. Whereas Nomad takes a completely different approach. So Nomad provides this sort of wonderful persistent archive of basically anyone's data. Anyone who wants to give it, they will probably, if you ask them, they'll write a parser for whatever code you've come up with. If you ask them very nicely anyway. And they will archive this data for you for probably 25 years is the minimum. I mean, Patrick, I don't know what the official agreement is, but there's, they are a very official data repository.
Yeah, it's 10 years from upload.
10 years, oh, okay.
Minimum.
So, this is then becomes, it's a completely different beast in some sense, right? Even though the sort of the same abstractions there are crystal structures, it's, when you're querying Nomad, you're essentially looking for work attached to a particular paper or some particular method or particular code. Another example would be the COD, so the crystallography open database, which is this very sort of long running, it was somewhere down the far left of the first picture I showed. This curated set of experimental crystal structures, which were kind of ingested through the literature. They had agreements with a series of journals. So lots of overlap with the ICSD, obviously, but completely sort of free and open source. And primarily, yeah, from I guess, XRD characterization of the structures. The point of me listing these is just to show you that these three databases are in the OPTIMADE consortium. They all serve data through OPTIMADE, and they're completely different. You would use them for different things, but having this unified interface, as we'll see, hopefully can be quite powerful. And then the fourth example, just to maybe hammer home that we are just a bunch of people, is this ODBX database, which is basically just some stuff I did. That's it. It's just some crystal structures. I mean, I quite like them because I worked on them, but maybe no one else is interested in them. But through, as we'll see, through the approaches we came up with, or through the expectations we set out in OPTIMADE, if someone queries the sort of OPTIMADE consortium databases, so my database results will appear alongside Materials Project, and maybe because of what I did in my PhD, so crystal structure prediction, maybe I have one phase diagram that's really, really well sampled compared to Materials Project, and maybe there's new stuff in there that people should use in their own research. So we'll come back to that point later on, actually. And I made this up. I made these three words up about 20 minutes ago. I think it kind of summarizes what we're trying to do, which is this idea of decentralized data unification. So the fact that, that I may have some small nugget of data somewhere, that unless I somehow get it into one of these big databases, whether it's through uploading through Nomad or through some other system, that data could just be sort of lost somewhere. It could just rot as an archive on like a generic repository or something like this. But with OPTIMADE, you will be able to sort of filter that data and get it in front of the people who are interested in, in searching for it. Hopefully, we'll see that the whole becomes greater than the sum of the parts, I guess, would be the sort of trite way of explaining it. Okay. So just again, a quick example to emphasize the point about different sort of syntax and different sort of practical issues. Let's say you wanted to find crystal structures of silicon dioxide in 3 semi-randomly chosen databases. For example, AFlow, Materials Project, and COD. So these 3 URLs are what you would need to sort of give to whatever client you're using to access this data, whether it's your browser, whether it's some sort of command line tool, something that can do HTTP, basically. And you'll see they all look kind of different. So the AFlow, you have some stuff at the start, which might make sense. You have AFlow/API. Cool. You then have this thing called aflux, like, okay, don't know what that is, but cool. And then you have this query parameter. So a question mark indicates that we're now sort of querying that aflux endpoint for things that have silicon, oxygen, and 2 species. And you might think, well, there's lots of things that have those that aren't silicon dioxide, but it turns out the way that AFlow represents their data, you would have to then do an extra level of filtering to then just get things that are in a 1:2 ratio. Although I think maybe last time I said this to them, they said, oh, we can do that now. So this is now a slightly outdated example, but hopefully you get the gist. And then Materials Project, there's something else going on. So now the purple bit, the sort of base of the URL is materialsproject.org/rest/v2. Yeah, you don't necessarily know what v2 is, you rest, maybe we're going to hear about in a second. You then want to query the materials endpoint, and then you put in your formula, it's fine. And then you put in vast for some reason, even though you just wanted the crystal structure, and then you put in structure. Okay, sure. So there's something going on there, there's some domain knowledge of, oh, they use vast for this that I have to know about. And finally, COD. So again, crystallography.net/cod. Fine. Just give you that start point. Their endpoint is called results. And again, you provide it as a query parameter. This time you have to do O2SI rather than SiO2 because they choose to order their things alphabetically. And if you're very keen-eyed, you'll see a space between the O2 and the SI, and the query doesn't work otherwise. And if you put it into a particular client that doesn't escape spaces properly, then you have to figure out why it's giving you some weird error, blah, 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 blah. And also by default, the COD it returns hypertext, it returns HTML, as all good websites from sort of 20 years ago do. So you have to ask it to do JSON. You have to ask it to get a JSON response back, which is kind of implicit here that all these other APIs at the moment are JSON APIs. And I don't know if it's worth sort of laboring the point when going to these actual URLs and showing you, but you can imagine that the actual response you get back as well is completely different for each of them. So, they all have different representations of crystal structures, which is completely fine. But if you actually then want to take these and use them, you're going to have to somehow map them all individually to whatever model you actually want to use. And yeah, if you want to then extend it to another 20 databases, that's a lot of extra work for you. And then if everyone else wants to do that, it's a lot of extra work for everyone. So you end up with sort of fracturing of the community of data. So how do we make this kind of thing, this kind of approach of either mapping the data automatically or figuring out what these URLs should be in order to get what I want? How do we make this what I'm going to call machine actionable? So how do we make it possible for, let's say, an autonomous agent that knows about crystal structures but doesn't necessarily know how to get all these data out? How do we make it possible for it to explore these data sets? And I guess typically we would download the whole data set and then map it to our own model and let our models do whatever they want. After that, I did ask ChatGPT how to do this, and I kind of want to show you actually because it was kind of interesting. I won't type it all out again, but I asked it to give me some SiO2 structures. It told me about a few of the databases we mentioned. Like, okay, cool. Can you give me the JSON API for it? And it told me to go buy the CSD, told me to go buy the ICSD, which they're on solid legal ground there. It told me the documentation for the materials project. Cool. COD, I got pretty close. So this at least gives you the HTML page I mentioned. And then it turns out it also apparently knows about OPTIMADE, which is a bit scary. So I asked it, had it heard of it? And it basically then made up a load of rubbish about materials project and how you would access materials project through OPTIMADE, and saying you need an API key and all these various things. But it got pretty close. So this is the OPTIMADE URL it suggested, which is actually bang on. It does something a bit weird here. I'm not sure that's the right escape characters for double quotes, but I think that might be single quotes from memory. And also, as we'll see, we can be a bit picky about, again, our ordering of formulas should be alphabetical in order to make filtering easier. I just found that quite interesting, I guess, that it's picked up on that already, given that we only published the sort of first release in 2020 and paper was in 2021. And then I asked it what you would actually get back from that endpoint. And it's pretty close again, so it's correct up until here. And then it just kind of goes a bit off and makes up some stuff. But it's all fairly feasible. I mean, maybe this is actually a better idea than what we ended up coming up with. So it's scary.
This is now the tutorial.
Yeah, this is, so I'm going to sit down and whenever you ask me, I'll just type straight into ChatGPT. Yeah, don't ask Bing anything about that because I don't want it to know about me. I don't want it to know about OPTIMADE. I've seen what it does to people. It follows them online and tries to make them eat their wife. Okay, so to sort of now just give you a quick demo of how this kind of thing would work for OPTIMADE. Hopefully you can see that properly. So this is just me and my terminal. Don't look at the time I did this because it's embarrassing, but it was quite early this morning. And what I've just done there is use a particular client that we've developed. I've just entered a filter, and that filter string has then been sent to all these different databases automatically. And hopefully you saw the progress bars all happening at the same time, which was some extra amount of work to do. People know about async Python, it's lots of fun. And you'll see what I did initially. I mean, I'm just going to have to loop around again, I think, to actually show you again. But I asked it to count how many results are in each database. So the first set you saw there was just a number, it's how many results were returned for that query. And then what I've just done is told it to give me the structures, pipe the structures to a JSON file, and just get it in terminal. So it's quite handy for sort of little exploratory queries to all databases. I'll just let it play through one more time so you can see what it actually did. And this is going to be sort of, there's a brief tutorial part on this particular code. So what I've done is I've asked for chemical formula reduced equals O2SI, which, as I say, has to be alphabetical, just because. I've asked it to count rather than just guess all the results. And that's basically all the OPTIMADE databases, the whole OPTIMADE consortium. You can probably recognize some of the URLs there that I've already mentioned. And then again, just to show you, you can also pipe those results to a file. I think I tweaked the query a bit, yes. Also asked it to give me anything that had less than 50 sites in unit cell. Maybe I'm going to run DFT on this, and I don't want to waste my computer time on this. Okay, that's probably enough of that. So to sort of recreate the map from Lowry's lovely paper, this is every database that currently implements OPTIMADE, with a bit of cheating on ones that have kind of 90% done it. I hope will be over the line fairly soon. And I think I have an animation. Should have played. Okay, wasn't that impressive an animation, but basically you can see again these names that I've been mentioning. So in the States, we've got Materials Project, Aflow, OPD, the dots from memory, also Jarvis as well. And the unlabeled dot is probably you can say that it's the metaverse database of shipping on, which is a sort of purely hypothetical machine learned set of machine learning relaxations from this universal M3GNet essential. It's quite an interesting one, I'm quite excited about. And then in Europe, we've got quite a strong presence, I guess. So Nomad out of Berlin, Materials Cloud in Switzerland, COD in Lithuania. I guess the furthest north, closest to Finland, was probably between the COD and HTTK, which is from Linköping University. And then, as I say, the one I worked on in my PhD, ODBX. And then my favorite one is this one, because one day we just got a pull request and they just added the link to our repository and they just had an API and we just never heard of. Well, okay, we'd heard of the database, but we hadn't heard anything from them that they were doing anything, and everything just seemed to work. So this 2D materials encyclopedia out of I think it's National University of Singapore. So yeah, that was sort of the first real success, I would say, that we had in spreading this out beyond the people that actually came up with it. Okay, so as of 2020, this is just a little snapshot of the kind of numbers we had in the database in the consortium there. This was in the sort of the first paper we published in SciData. There'll be a link to it somewhere later on. These 3 queries that we wanted to run against every database to sort of show that it's possible. And from memory, I think, well, can I even remember? The first one was looking for a set of elements in various sort of intermetallics. The second one was those elements, but with more than 3 elements in the unit cell. And then the third one was more than 2 units in the unit cell, same elements, but no lead. So slightly more sort of complicated queries building up. And there was a bit of a palaver, I guess, because everyone wants to have the biggest number on this. And I guess Nomad kind of cheat because they take everyone's data because that's their job. But you have to sort of avoid being ego-driven in this, I guess, which I proudly did with my ODBX database, serving a whole 0 results for one query and sort of 50-ish the other ones. And again, that's just to sort of emphasize that it doesn't really matter what scale you're at. You can post one of these things and people can use it. And yeah, sorry, here's the sort of the citation, I guess. There is a proper link somewhere else. This is again just to show that it was really a community effort. This is most of the representatives from the databases I just showed. But these are the ones that sort of directly contributed to the specification or the OPTIMADE APIs of those databases. So yeah, I think that's in the end. So to bring it back to sort of what actually is this? As I sort of introduced it, it's just some words, but what do those words say? I don't recommend you read them. So I thought I'd sort of briefly introduce some more of the technical aspects, I guess, before we dive into that. But it seems like we're quite familiar in this room already with this sort of the concept of like APIs and HTTP and REST, and then we'll see a JSON API. So I'll just kind of whiz through this, and feel free to ask if you're not sort of familiar. But I've sort of summarized it here that an API is when your code calls someone else's code. So it's an interface that's provided that lets you do more things than you would sort of bother to write on your own. And the idea is to expose the functionality of that code rather than without having to care about the details of how they actually implemented it. And an API specification, which, as I've said, is the sort of the 25,000 words. It defines this sort of set of expectations or promises about what happens when you do something with that API, basically. So some examples of that kind of level of abstraction. So you're probably familiar with scikit-learn in Python, which it uses NumPy. It doesn't go and re-implement the wheel and doesn't care about doing some of the arrays. It just does machine learning. It works at that level. And then NumPy itself is just it's a wrapper for an even older library of a completely different programming language. But because it exposed such a sort of solid, I wouldn't say usable. I don't know if anyone else has used BLAS before, but it's pretty sort of archaic, I guess. But NumPy didn't have to worry about the actual real sort of details of the BLAS implementation, and that allows it to be sort of much more expressive and more powerful in doing what people actually need to do. It's exactly the same with how we should view these sort of web APIs. So yeah, a web API is sort of the equivalent of calling someone else's code on their computer. So you're not, you're doing something that you want them to do, and it's setting off some machine somewhere that you're you're sort of not at, it's their computer, and something is happening as a result. So it's sort of very vague, but that's ultimately all it is. And they're everywhere. So these kind of well-defined interfaces sort of run the world now, really. They certainly run sort of the internet. When you're doing things like online payments and OAuth across different providers, sort of login via Google, any kind of database queries, any kind of offloading of operations in the cloud, and you know, more machine learning oriented things like face recognition and translation and so on. These are all working with these sort of well-defined, often web APIs. Yeah, and this is kind of getting more to the bare bones, I guess, but just as a bit of context, I mean, the way you commonly control a web API is by using HTTP, and HTTP defines these sort of set of magic words that do things. We're only really going to care about get in this particular sort of session, which, as you might expect, is what you ask when you say, give me this piece of data. You shout get, you always have to shout them, they have to be all caps. Be sort of firm with these APIs. And you would access them with basically whatever tool you want, any tool that works with HTTP. So don't feel like in these tutorials you have to use Python or anything. You know, you can just type in URLs in the browser and you'll get the same thing back, just sort of rendered in a different way. Or you can use command line tools like curl or wget, which often is actually what Python would be using itself under the hood to make these requests. Yeah, so I mean, some sort of silly examples of things you might do and what they look like, which I will not go into. But I did animate apparently. Okay. So the final point I wanted to build to is what a sort of REST API is. And it's this sort of nebulous thing called the representational state transfer API, which just means basically a stateless API. So you can ask for page 2, then you can ask for page 3, and it's probably got to you're just then getting whatever the third page was at that time. Some of them do slightly smarter things, but yeah, that is completely valid. And typically the way these work is that you just combine these different methods on the left into sort of little subprograms, I guess, that do the things you want. So you can manipulate resources on that server, whether it's just getting them, whether it's changing them with posts, or putting new ones on there with puts, or deleting them with deletes. So you get the idea. And yeah, OPTIMADE in particular is just based on this specific flavor of REST API called the JSON API, which is kind of the NumPy Blast equivalent for us, I guess. So we didn't want to reinvent the wheel for JSON APIs. We just found something called kind of confusingly JSON API and used that, which has this nice sort of common structure, and means again we can make the use of all the tools that obey that interface. So you can even, if you write a sort of your schema for OPTIMADE in a particular way, you can just give that to a code generation program, another program, and it will basically write you a web server that implements that API. I don't think anyone's tried that or done that because it's probably doesn't work that easily, but that was the kind of intention we had. And there's thousands of things that use this JSON API format. Okay, and yeah, there's ways of describing it. As I say, if you write the schema with OpenAPI or JSON schema, then you get another sort of level of controllability. Okay, so this is kind of just a vague summary of that, of how a server, which is just running a database, would serve data to people on the web. The key thing to take away from this really is that when I say that a server implements an OPTIMADE API, that isn't instead of what they were doing before. It's and as well as it's like another language that that server speaks that people can use to interact with it. So often these databases still have web UIs, they still have a very database specific UI, API, which is the one that often they're using under the hood themselves. And that's the one that is actually closely mapped to their data model. And often you can implement OPTIMADE as a kind of translation layer on top of that, which just gives people sort of unified access. Okay. That time's flying by already. So, the API format itself, I'll just briefly go through that before maybe showing you some more demo style things. So as I say, we released the version 1.0 in 2020. But remember when I said we started in 2016, so that was a bit of a slog. Took 4 big annual meetings, so week-long meetings in Lausanne, and then basically met every month in between all of those as well, with some subset of those people on the paper. So it's quite a lots of arguments, lots of things about what is a crystal structure, what is an atom, what is the position of an atom. I mean, the mind boggles, I guess, at what you can disagree with. But in the end, we were trying to come up with something that was flexible enough that every database could implement it, and it could be extensible in the future. So we wouldn't write something that when OPTIMADE 2.0 comes out, we just have to throw everything else in the bin and everyone else has to re-implement things. And that's really sort of the key to the design we came up with, is extensibility. So, I mean, I've said this, but just to hammer it home again, OPTIMADE is a REST API specification for access to crystal structure databases specifically. It's this human readable specification that has this basis in JSON API. And if you're a machine, you might want to read machine readable schema. It does enable this unified access to many millions of crystal structures. That's kind of just there right now. And I guess we'll see in the tutorials that one of the difficulties, we don't want to force people. There's no punishment if your server goes down, right? We're not about that. It's a case of writing your tools in such a way that they can be reactive, or at least sort of accommodate the database being down, say, or sort of inconsistency somewhere. We're not, we're strict enough that this thing sort of all works, but we're not super strict that it becomes a huge burden on people. But the one additional thing we have on top of the API definitions is this federated providers list. So this is the thing that I said that the 2D materials database just sort of added themselves to one day. And this is, I think, key to how it's sort of growing going forward, is that anyone can join, and if you join, you're instantly sort of served whenever anyone tries to query sort of the entire set of providers. There's no sort of lower bar you have to pass. I mean, it would help if you had an OPTIMADE API at the URL you said. We'd probably check that bit first, but if it's close enough, we'll probably let you in. And really, the idea is that can then grow from there, from sort of smaller groups contributing data, and it doesn't become this big sort of monolithic thing of the big databases. To get your crystal structure in front of someone else, it has to be one of the big databases. That this is kind of circumventing that. So we have lots of tools as well for validating APIs. So although we don't sort of tell you off for not getting it right, you can at least see if you're getting it wrong, and that can help you with development. So in terms of the features, I mean, maybe slightly underwhelming. We define a whopping 2 resource types: crystal structures and bibliographic references. And those are about the only 2 that are actually common to all these databases. As I say, everything else is built through sort of extensibility. Probably the one thing that separates us from, one of the things that separates us from having coming up with a new file format and just serving that, is that we define this full grammar for filtering on OPTIMADE data. Maybe I'll show you that in a minute in the demo, but the whole sort of construct I showed of asking for a chemical formula being equal to something. To be able to pass that, you have to know that chemical formula is a thing, that you have an operation equals, and that if you give it a string, that has to be converted to a database query that will do what it says. So there's quite a lot of machinery just to sort of get that bit going. And that's the difference between just putting a load of files on a disk and making someone download them and look through them. Is really this filtering. I've mentioned extensibility already a few times, and basically you report how you're extending OPTIMADE through this info point, which is also quite simple for a human to read. And there's some sort of concept of version negotiation. But the key thing as well, in order to get this to work for, let's say, sort of 22, 23 databases, the format has to be strict enough to be useful, but flexible enough to actually be used, as it were. So we're not asking people to delete columns in their databases or something if it can't be fit into OPTIMADE. It really is a case of there's actually only one field that's mandatory support, and there's just a well-defined way of saying, I don't have that field, tell the client to sort of go away. But often you find that, most databases implement most things, so only sort of a few edge cases, often for very sort of subtle technical reasons why they can't do things. It's good to have that flexibility. Yes, as I say, but hopefully not just another format, because we have this extra layer of filtering, the well-defined way of laying it out in terms of URLs. So you know that, as we'll see in a minute, if you have the start of the URL, the purple bit from the slide a few minutes ago, then everything after that will be the same for all databases. So you just send the same, I can't remember the other colors, but you send the same end of that URL, and it should work for all of them. Well, in fact, it does work for all of them. So onto what you'd actually get back. I mean, I keep mentioning JSON API. If you don't know what that is, it's not very useful. But if you do, I'm sure. But basically, the key thing is that every response is broken down into these well-defined keys. So data, surprisingly, contains the data, the actual crystal structures, or references, mostly crystal structures. Links are doing things like providing a URL to your own database's API for that particular entry, or providing a link to someone else's database if you want to be sort of charitable and direct people away from your site. This thing will be included, which lets you link resources together. So perhaps if you had a structure that was on your SSD and then you ran, I don't know, cluster expansion or something on it, and 2,000 different orderings or whatever it is, or configurations, you could then link all of those structures to the top one and add an extra sort of hierarchical layer to the database. You express it with it. And the meta is just kind of expanded whatever metadata you want. And then every data response, so every sort of structure, is broken down into these 4 keys: type, ID, attributes, and relationships. And really, the important ones are ID and attributes. So ID should be a sort of globally within your database. I guess that means a locally unique ID. So you can't have multiple things with the same ID in your own database. Then all of the sort of science, all of the actual domain-specific data is in this attributes field. And I guess, as I say that, it sounds kind of cumbersome. Why do we bother doing that? Why don't we just have first field as position, second field as elements, whatever? That would be much more data efficient, bandwidth efficient. Sure, but having this sort of more rigid structure allows us to do way more things with it, I guess. So, said a lot of this already about the entity types, so I'll just sort of skip through this. The structures served at the structures endpoint. Most fields aren't mandatory, apart from this one peculiar one. References kind of just follows what you might expect. It follows like a bib JSON specification, which itself follows whatever biblatex did sort of 60 years ago. That should be fairly legible. Okay, yeah, so we use this custom grammar, as I said. There's lots of examples of it in the specification. We do want to dive into that, but hopefully the sort of the stuff we'll work through in the tutorials will also give you a feel for how to do this. As a sort of technical, practical point, you do need to be quite careful with encoding your queries, I guess. So by that I mean, depending on the tool you're doing it in, you might have to put quotes around the whole thing. You might have to worry about what space looks like. In reality, it's going to get converted by the tool into something that's URL safe. So it's going to have %20 every time you put space and whatever it was, %22 for quotes. So I basically just say use a tool that does that for you. You don't have to worry about it. And yeah, these filters should be transferable completely between every database that implements them. And hopefully, as we go forward, people implement more of the provider-specific data they have. As we'll see, so things like energies, we didn't really pin anything down on that because I mean, what is an energy for COD? They have a diffraction pattern that they're converted to a crystal structure. It doesn't make sense for them. That already can't be a mandatory property, even though that's probably the thing that most of us are interested in as theorists or as machine learners. And each entry type, as I say, you can filter in two different ways. So just to remind you, entry types mean structures or references. So if you want a single structure, just do slash structures and then UID. You already know UID, of course, and that will give you one entry back if it exists. And then to actually apply these filters, what you would do is, again, slash structures, and then this query parameter filter. That's where you would write the sort of the magic OPTIMADE string that does your query. So something like 4 in 1 and then is equals 2. Okay, I think this is my final point on the actual format itself. It's pretty dry. One other aspect, as well as the provider list, is this concept of index metadatabases, which are confusing to people who are trying to use this for the first time, I guess, but very, very boring. So I will just spend the shorter time as I can explaining them, and maybe the rest can be explained through questions. But essentially, the URL you get from the providers list isn't to a real database, it's to an index metadatabase. And that index metadatabase allows people to have multiple databases or one database. And when we designed this, we decided that even if you just have one database, you need to have an index metadatabase. So we have lots of sort of, I'm at this URL, it's not giving me anything, it's giving me strange results. Oh, I'm at the wrong one, I need to go to the main database URL. Hopefully that becomes clearer as you work through the examples. Hopefully, actually, you don't even see this going on, it's the clients sort of do this for you. But if you do get stuck, this may be the sort of what's going on. As I said, I've already mentioned links, and that's how you would sort of tell people other databases. Info is where you list your particular metadata for your database. And that's also where you would list things like, I'm defining an energy to be, my underscore DFT underscore energy. I'm going to serve it with that field name. And if you query just my database, then you're going to see those fields and you can use them whatever you want. But you're probably not going to find them in anyone else's database under the same name unless you go and sort of look them up. And again, we'll come back to how we maybe extend everything together rather than everyone defining their own fields. That's sort of an ongoing thing. Okay, so that was a bit of a slog, I guess, for the first 50 minutes. I'm already starting to lose my voice. So I guess first thing, are there any questions about the whole sort of concept, I guess, first maybe, and then maybe if there's any technical questions, they can be pushed further to the end of the session. I can see the chat as well if anyone wants to put anything in the chat. I'll maybe just give you a minute or so. Yes. Hi.
You pull from multiple databases, and is there any way or any, let's say, a way from OPTIMADE to check whether the same structure has occurred in all databases?
Yeah, that's a good question. I'll be very pedantic in my answer. So I don't pull from everyone's database. You do. I don't pull from everyone's database, or OPTIMADE doesn't. You're the one doing that. So the client knows about the consortium. I know you probably understood that, but just to make it clear to everyone, the client knows that all of these databases exist and takes the data locally, as it were. And then to answer your actual question, no. So it's, structure matching, I guess, is difficult. There's lots of ways the database can provide that additional data. So if it knows it took it from the ICSD, maybe did a DFT relaxation on it or something, then often you would preserve that ICSD ID in your database entry, so you can match that in that way. In a perfect world, they would link to that system URL or ICSD entry. I'm not even sure those exist. I guess you could make one up that's ICSD : and then the collection code or something like that. But there's no sort of super standardized way of doing that. What we'll see a bit later on is that the way this is probably going to grow is sort of sub-federations of databases coming together and saying, oh, I also pull data from the ICSD. Let's agree between you and I of a format to represent that. Which avoids having these in sort of lockstep arguments of 25 databases need to agree on one thing. I think that's going to be a powerful thing in the future, sort of little sub-federations. Does that answer your question?
Yes, thank you.
I mean, of course, you could filter locally on with your own tools. As you see, it's integrated with things like PAMAGen and ASE. So if you have a structure matching algorithm in those, you can just run it directly. Just going to check the chat here. Oops. I don't think there was anything.
No questions.
Yeah, sorry. You can just see a notification on this one, but it's absolutely old. Okay, actually, so I'm going to sit down then. I'm quickly going to show you what some of this looks like. Maybe show you some links and things. So actually, what I'll do for my own sake is skip to the next slide, which has all the links I was going to go to. So if you're already bored of me talking, I mean, you can just look at these links yourself. We have a homepage, unsurprisingly. Lots of links out here to things like the specification. When I say don't read it, I mean really don't read it unless you're actually implementing it. And even then, probably don't read it. But it's on GitHub. Everything we do is on GitHub. Obviously, this only works as an open source project. But these are those words that I mentioned. It reads like an API specification would read. In a bad way, or in a good way, I guess. Not much use to be sure of that still. Struggling to go back to my slides. Okay. One useful additional site is this provided dashboard. I'm getting confused because this number seems to be changing quite a lot of them, which means that I think some databases are maybe up and down for maintenance, which, given that I told them I was doing tutorials today, is very kind of them to do that today. Please believe me when I say we had more structures than this last night. But this is the sort of an automatically generated dashboard of all the people that serve OPTIMADE data. So maybe I should just give them all a shout out, I guess. I mean, AFlow, CCP&C database, there's a sort of UK NMR thing that's being developed. COD, Jarvis, MacCloud is a database out of China that I think they maybe implemented OPTIMADE, but no one can tell because you need a Chinese mobile number to get access. And one of the developers gave me his mobile number to do that, but we kind of lost touch. But yeah, it is somehow also not just public databases doing this, also private ones in private countries. So Materials Cloud out of Switzerland. I mean, this is an interesting one because they're probably the primary user of this index thing I mentioned. So they actually have 10 databases that they serve. And that's because to them, a database is a static data set that someone has archived in Materials Cloud. In fact, we'll come back to those in a second. Just go to the bottom here. So materials projects, MPDS, which is, I think, the kind of like official archive of a sort of polling file, and Spring Materials, ICDD, ASM, Medea, Pearson, blah, blah, blah. Lots of commercial databases, basically, they have an agreement with where they serve, I think pretty much all of the actual structural information they serve through OPTIMADE, but then other stuff you have to go and sort of get a license for. So again, quite flexible to that kind of thing. Nomad, ODBX, the OMDB out of Entropic, QMD, TCOD, 2D Mappedia, and then a few different tools that aren't strictly databases, but that interoperate somehow with OPTIMADE. So probably heard of AIDA, the high throughput toolkits. I think there's an ASE pull request somewhere for working directly with OPTIMADE as well. But just to dive into one of these, so Materials Cloud is probably the best example, and it's the most exciting. So if you actually go to their entry on the dashboard, you see all of their databases listed. Picking on one, I can see at the 2D materials, 2D crystals database. So from memory, I think this is one of their big sort of landmark papers where they did this sort of computational exfoliation, they called it, of every known compound, I think, and came up with a load of stable 2D materials as predicted by DFT. You can access those, you can filter those. You know, the format that we came up with is completely flexible for things like 2D materials, also 1D materials, 0D materials. It's not just 3D crystal structures, even if that is the majority of data. And you can see there's some moths and things down here. There's all kinds of fun stuff. And actually, annoyingly, so you see this validation thing where they pass all the tests. So I was going to show you what it looks like if they don't pass all the tests, but can't. So I'll have to find one that isn't passing the tests. And it's probably only fair to pick on my database, which I'm sure is not passing all the tests. There we go. So it's failing a few. And what this is so we have this API validation tool where basically every morning at like, well, I guess it depends where you are, but around 6 a.m. for me, anyway, this script runs on every database. It queries, well, it checks all their metadata is correct, to some definition of correct, asks them what kind of fields you can get from their database, and then just starts doing almost random queries, checking that they're consistent with the filters you give it. So, if I ask for silicon dioxide, I have to check that everything I get back is silicon dioxide. If I ask for number of elements being less than 3, then I should make sure that that's a stupid example, but it does some fairly sort of smart things about making sure that queries don't overlap if they shouldn't overlap. And that's what these sort of tests are. 63 different tests this one came up with. So if you're running into issues with the database, this is often a place to just check and see, is this like a known problem? You can often sort of have a go at the person doing it. I mean, in this case, this is, so I wrote the validator, so I can't really complain, but this is a very picky error where I didn't apparently, that maybe this is outside the level of specification that you can't say you're serving a dictionary at the moment for some reason, or you couldn't in this particular version. So it is very sort of pedantic about the format. But there is no consequence to this. This has been broken for probably a couple of years. And I know that it doesn't affect anything, so I'm fine to leave that. Okay, so that's a bit of a tangent. For some reason I can't click on that button. So let's just very quickly go through what a JSON response looks like. I'm going to talk you through this. It's probably better just to show it in the first place, but never mind. So this is probably you won't be able to read the URL here. This is optimade.odbx.science, which is the base URL /v1/info. So this is the info endpoint. And the kind of info you get back is what data am I serving, what version of Optimade am I using, a little description of what is actually in the database. So I'll have a slide or two on this later on, so I won't read it all out. Things about the implementation, who you would contact if there's a problem with the data. I'm then going to add /structures to the end of this, so now info/structures. This is telling me about all the fields that are served for a particular structure. Either by so under the properties key, you'll see these are all the fields that are served. Anything that doesn't start with an underscore, or actually underscore ODBX, is an Optimade standardized field. So I didn't want to list them all earlier on, but you can see them here. You can see the kind of things that we've standardized. Most of these are standardized in such a way that you can then filter on them across databases, as I say. So there may be some redundancy between dimension types, which is a kind of like the ASE PBC style thing, where you have basically a Boolean value for each dimension, whether it's periodic or not. Then we also have an n-periodic dimensions, which is just, I guess, the sum of those values. But you can see that those both fill different niches of being able to query things like slabs without caring whether it's a slabbing XY or XZ or whatever. And then maybe more exciting, some fields that I serve in particular for my database that you might also find in other databases. So some standard stuff like cell volumes, but things like DFT parameters. We'll see an example in a minute. Easier just to show you an actual entry now. Let's just go to structures endpoint, which gives you everything by default. But if you don't give it a filter, so this will be the first page of results. This looks like lithium, very exciting. But now you can see some of the information I just showed you. So space groups, the tolerance I use to compute the space group, this kind of thing, commit version of cassette that I use to compute this thing, and then some actual sort of DFT results. And you often find that most databases do have this information served through Optimade, but everyone does it slightly differently, to the point of it being slightly annoying to use. Okay. So the one other thing I wanted to do there is show you a filter. So now on the structured endpoint, I'm just going to add filter equals, let's do elements as tin. I know that's in there. I double quote around SN. And I have this sort of list operator has, which checks if the string SN is in the elements list. And as you see, you get something back that has tin in it, thankfully. But the sort of the big wow moment, and I want an audible gasp as I hit enter here, is that I can now replace this part of the URL with the materialsproject.org and pray that it's not down for some reason. And hopefully this query will work. So there we go. I mean, it has things with tin in it as well, unsurprisingly. But as you can see, this is kind of the whole point, right? Is that we can do these queries across different providers without really any effort. And we can now then build sort of layers of tools on top of that. Hopefully, as we will see in the tutorials. Okay, so I'm 1 hour in. There's the clock.
So the coffee break would be scheduled for 3:20. So if you still have something, you can go out.
Yeah, sure. Yeah. Okay, yeah, we'll keep going for another 10-15 minutes, I guess. Yeah. With some common pitfalls. I'll stand back up again because my leg is going dead. I'm very old. So yeah, I've already mentioned this one. If you just tried to visit that base URL, so the one I was just on, sort of all bets are off what you get back. I could put, well, someone could put something at that URL that could be completely unrelated to Optimade. I don't know what kind of example I was coming up with there, but you know, don't worry about it. The key is to remember that you should always go to the version endpoint you actually want. So something like /v1/info, something like that. Already mentioned this one as well, actually. So visiting the wrong URL or the wrong base URL. You visit the one that's called base URL for an index metadatabase, confusingly, then you end up in a bit of a mess. You have to sort of find your way out. Basically, just use a tool that already knows that, or know that you have to go to a particular database that you want. So as I said, some providers have multiple. It's good to know. Already mentioned URL encoding. Good. So use something like, I mean, the most basic thing would be to use URL lib in Python standard library. We'll sort you out. And I think I added this about 20 minutes before talking. It's a common pitfall to think this stuff should be interesting, I guess, that you should be able to do cool things with it. It's really boring. Like, I hope like you don't think I think this is interesting. Like it's meant to be so simple and so boring that you can build layers of it on top of things. Right? The application is sort of, I don't want to get carried away, but sort of emergent in what you build from it. Okay, so, and I think that's sort of, we're at the stage now with Optimade that it's relatively stable, the data's all pretty much correct and valid, and we now need to build things with it. It'd be great if I could have the time to do that myself. So I probably have got time to go through the applications before coffee break. And these are just ones I've kind of, well, through discussion with other people as well, come up with as potential avenues of where this could be used. Somewhat in the context of this conference, I guess, with machine learning and active learning, slightly more specifically. So I can't remember what the first one is, so let's get it up first. Yeah, so it's kind of like an open question. What would you do if you had this kind of unified access to what I think I can say is the largest data set of hypothetical, reported, whatever you want to call it, inorganic crystal structures? Hopefully quite a lot, but it's always going to be super field dependent. So I think we've seen in the other tutorials already, so the methods, for example, that Bjork showed yesterday, fantastic approaches for generating, well, across, I don't want to diminish the domain of the scope of the things he showed, but you know, if you were trying to find a structure of, what was it, 13 palladium atoms on a surface, probably no one's done that in OPTIMADE, so it's not actually that useful to you. You could probably get the bulk material, and then maybe someone comes up with a nanocluster database, and then you can do something, maybe chop it in half and stick it on a surface, and you could use it in that way. But you know, if you're not working this kind of global regime, I guess, of 3D crystal structures, then maybe it's not super useful to you until someone gives you that data, or until you put that data there yourself. So yeah, as I said, so surfaces, interfaces, amorphous things, it'd be cool to have them in there, because I think people spend a lot of time computing these things from scratch. You know, coming up with an amorphous model for material, a good one, is difficult, it's problem dependent, it's method dependent. You know, curating databases of that could be a useful avenue. Things like molecular crystals and MOFs. I mean, I showed sort of one example of a MOF database, and I guess the COD has a lot of experimental molecular crystals. But if that's your domain, then yeah, maybe the data just sort of isn't there in OPTIMADE at the moment. But yeah, so moving on to these sort of 3 headline applications that I've tried to tie together slightly thematically. The first one I'm calling materials discovery, which means many things to many people. So you know, it could mean coming up with a new structure that's stable in DFT and sort of calling it a day. It could mean forcing your experimental colleague to actually try and make it, and then you know, maybe it doesn't exist, maybe it can't be synthesized. But what I'm kind of interested in, or the context I think OPTIMADE is powerful for, is this idea of why we're filtering just on known materials when we do these searches. A particular case study I want to show is not my own work at all. It's this program called Xeris from a PhD student, I think it's now finished, Pedro Baptista de Castro in MIMS. And it's this automated XLD refinement thing that uses existing structured databases, does some queries, makes a local cache of things that are relevant to the system that the experimentalist is looking at. And then you give it your actual measured XLD, you know, as it comes off the beam, as it were, and you sort of automatically screen and refine all of the sort of proposed structures in you know, you call this in the literature, I guess. And then the sort of thing, I guess this has been done in the past for different, you know, the ICDD and various other diffraction-specific databases. So Xeris ties it together and had interfaces to the AFlow, OPMD, Materials Project, COD, quite a few. And so the value had probably 3,000 lines of Python to actually interact with those databases all sort of separately. And then I kind of saw this on GitHub and just thought, well, let's do one OPTIMADE interface for that. And it just works. It was sort of a few lines just to use the client that we already come up with. So automatically, you're getting access to this wider pool of structures, and maybe most of them are garbage. Right? Maybe it's just not. Maybe they're not useful at all for the particular problem. But sort of by virtue of how the method works, it's very cheap to screen. So why wouldn't we just try it? I guess I should say as well that the novelty of Xeris comes more in the fancy stuff. It does adaptive refining, and sort of various sort of Bayesian refining techniques and multi-phase fitting and things like that. That's kind of not the point of why I'm bringing it up. But where I see this going, so that's all well and good. We can now query more databases and less code. Sure, you could have just enumerated all databases that are in OPTIMADE anyway and used their APIs. That would have been completely feasible, just a bit more work. But I think the interesting thing going forward is going to be, you know, if we can get this sort of critical mass of people adding new data into OPTIMADE or new databases served with OPTIMADE APIs, then the day that, let's say, well, how do I do this sort of a company, let's keep it that vague, the day that a company decides it wants to do AI for science, I think that's not trademarked yet, then they come out with it, hopefully they come out with their OPTIMADE API, And it can do the stuff that the Bjork was showing. It does somehow know chemistry. And it can give you, let's say, random number pulled out of a hat, 31 million hypothetical crystal structures. And like, how do they get those in front of experimentalists sort of instantly in a completely sort of scalable way? I think ultimately would be the only way to do that. Unless, of course, they just sort of use their brand to say, well, you have to implement our API, which could happen. But I think this is, you know, this is probably my sort of favorite, sounds a bit like my personal interest in OPTIMADE is how you can just sort of plug in a new database, and it adds like considerably more value than just this database on its own was doing before. Like the database I showed for my work. And, you know, if I come up with one new crystal structure and that happens to be the one that's discovered by this system, then that's one crystal structure that wasn't there at all before. So you know, that is material discovery to me. So yeah, I think that the general takeaway there, outside of zero, is if you think you have some new stuff that you believe is sacred somehow, then you know, talk to someone in OPTIMADE or make your own OPTIMADE database. Just sort of do it and see what happens. It's, you know, it's fairly sort of low cost, and we're hopefully sort of making that cost lower and lower with the tools we develop. Yeah, and just also mention that so Full-Prof, which is another kind of workhorse XRD requirement code, I think is also having support for OPTIMADE directly. Oops. I was just going to say as well, so that this Zeros code is also open source and on GitHub. You want to check that out. This is definitely another late night or last minute stupid title. But yeah, I've said materials discovery ability or discoverability, which is kind of, you know, related to what I've just said, is this idea that anyone can turn up with anything. And there's a lot of words on that slide that I'll try and get through. But this idea of sort of having these federated databases rather than sort of centralized things, to me at least, it encourages this kind of early sharing and piecemeal sharing that, you know, if you're publishing a paper where you just saw one crystal structure, and maybe you weren't considering putting it in your ICSD before, maybe you don't think it's like ICSD quality somehow, or maybe it just takes too long to get in there, right? Maybe it takes 2 years. That could be 2 years that this structure was already in the hands somehow automatically without them knowing of an experimentalist using a tool that can already query OPTIMADE. And I would say that probably my personal contribution to OPTIMADE is around building these kind of tools that lower the barriers and hosting OPTIMADE data. Said drastically low, that's maybe overstating it a bit. There is still, you have to know Python, you have to know some stuff about hosting web servers and that, I guess. I'm going to do it all for you, but it's, you know, there was a lot of work for me to do that, so I would assume it would take someone roughly equivalent if they want to do it themselves. So the example here is that, you know, you propose a material through some calculation or something, and probably the standard now would be to stick it in Nomad, or if you've got like a well-defined data set, maybe you put it in Materials Cloud attached to your paper. And these, you know, Nomad is so big and great, you know, having this kind of persistent storage is absolutely like a cornerstone layer that we need in all of these, underpinning all of these approaches. But it can be then quite hard to sort of discover things within Nomad because it is so big. And similarly with Materials Cloud, so because Materials Cloud is a very generic domain-specific archive, so as long as it's vaguely to do with materials and it is like bytes on a disk, you can give it to them and they'll take it. And, you know, you describe your data in words, I guess. That can mean that you just, you know, you put it there and maybe someone sees your paper and they follow the links, but, you know, they have to see the paper, which is nowadays when there's something I can't keep up with literature at all. I wouldn't say anymore, but I don't think I ever did. It's just impossible, right? So having these kind of domain-specific things, these systems, these federations, or whatever in place that allow you to discover things in the data we're already publishing is, I think, super powerful. So yeah, I mean, again, not to sort of overstate what OPTIMADE is doing, but at least what we can do is if you're looking for a particular chemical space, then you can easily filter that. So we can't really do much about energies and things at the moment, which is obviously a big challenge. Will be very useful, but we'll see how that goes going forward. So, I really hope that we do get more small groups, like a research group which hosts its own database, and maybe a specific project would have its own database. I think we're going to see that going forward more and more, and as well, I hope we end up with, for example, integration of the ASE database. So even if you're not publishing it publicly, you can still use the OPTIMADE tools on an ASE database directly. And I know that some of the people in the ASE team already sort of working on that. I'm doing very well. I'm back to 5 minutes. Yeah, I've got like one stop. But yeah, I mean, I'm not saying that this is going to change the world. I mean, the pitfalls are that by being so flexible to everyone, someone could turn up and make a crystal structure that's 20 billion lithium atoms on the same spot, as long as it's representable with the OPTIMADE data model, which that would be, then make that create your million downloading 20 billion lithium atoms. Your client has to somehow know that, well, this, I don't want this, even if it's valid in some sense. It's not necessarily useful data, as it's somehow garbage. So with all these things, obviously, garbage in, garbage out. Goes without saying, I guess, nowadays. But I would say that there's a real opportunity for these kind of analysis methods, and particularly machine learning approaches to this. If your model can handle these multiple fidelities, then there's really like a lot of data out there. So let's say your particular approach, if you're training like something that can generate new crystal structures, obviously it's useful having energies to bias that towards low energy structures. But if you can somehow use this information of just what a structure looks like without it necessarily being stable, finding ways to use that kind of low fidelity data in some sense, seems pretty powerful as well. And hopefully, as I say, we'll keep, the OPTIMADE API is still going, it's still being developed. And as these new cases pop up, we'll try and be quite reactive to them, and we don't want to sort of stagnate. I'm not sure why there's an extra dot there. Forget that dot. Forget this whole right-hand side of the slide. But the final point was this idea of materials design. And then I think I was about to start describing my own research, which maybe I don't want to do right now. But this idea of sort of reapplying a lot of the high throughput searches people have done over the years. So it's quite common, I guess, nowadays that a research project tends to be take everything in the materials project, screen it according to some criteria that's like very cheap to calculate, whether it's, I don't know, cost or just particular set of elements you're interested in. That maybe you use some properties they already have calculated in there to further screen it based on band gap or something. And then you end up running, let's say, a few thousand DFT calculations or whatever's left at the bottom of your file. And often these papers get published, and all well and good. And you would say, oh, these are the 5 materials we think are best for this application. And then you sort of close the journal, and then no one's going to do that project again because it's been published. So I think with this kind of more dynamic set of data, I guess, that you can get through OPTIMADE. One thing I'm interested in doing personally is maybe just reapplying some of these high throughput workflows to an OPTIMADE query, which is, well, give me every structure that was added to these databases since this person did this study. And maybe these are all sort of hypothetical things, and maybe they're all sort of AI generated. Again, maybe it's garbage, but we have a fast way of screening it, then that could still be a way of getting to the high quality data we want at the end. So yeah, those are sort of the 3 that I wanted to discuss today. That probably brings us up to a coffee. If I could just have like 1 second.
Of course.
Not go through what I'm skipping through now. Just to quickly talk about these exercises. So I think, well, yeah, this is just spoilers abound. So just quickly how the exercises will work. So I think I've talked for long enough. We'll have a coffee break. Yeah, of course, if there are any questions, come up with them now. But there are a set of exercises written mostly by me, I guess, but also a few contributed by particular databases that want to kind of show off what they can do. And also a particular exercise on PyMatGen, by the PyMatGen team. You've already got the links, they're all on the ProLab. I think probably when we come back, I'll run through the stuff and just to show you where they all are. But I think the next session, I don't want to talk too much. It's going to be fairly informal, working through the exercises. I probably won't even do any coding to sort of show you stuff. Hopefully it can be a bit more sort of interactive. And then I'll just have a few slides to run through about midway through before we do the final exercise. So, yes, you have questions before coffee or?
So I had one. So your second example that you showed, that was really interesting. So is that tool already available? I couldn't find this discoverability. So if I discovered a material with DFT,
Yeah.
could I query if it's in any database?
So yeah, you could, yeah, so that's sort of the reverse of what I was suggesting, I guess. So I think I was suggesting that you would, if you've predicted something with DFT, you would make a database and tell people about it. Right. Of course, you can, if you
Tell them in a publication, but I need to make sure that it doesn't exist already.
Yeah, okay, so at that point, you can query all these databases for, let's say, a formula you're interested in.
So if you haven't written a tool that allows me to do it, I still have to figure out how to do it in OPTIMADE.
I mean, I could do it in a few lines to you in the exercises where it's, the point would be, I think, similar to in the middle there is that once you have the data of, let's say, the chemical space you're interested in, yeah, you just convert it all to whatever tool you want. So inline, you have ASE atoms, you have PyMagen atoms, you just do like a structure match or something on that much reduced data set. Yeah, maybe it's a couple of thousand, maybe it's 100,000, but it's hopefully not 26 million. So yeah, I guess that would be a perfect tool that someone could build this afternoon. I was talking about you. You've got lots of time. You're only organising a conference. Was there anything in the chat, or was that just the notification from? Good.
No, nothing.
Okay, well, let's go.
The hands-on tutorials will continue at 4
Yeah. See you again.
That's why I wrote them about you. I don't know why it's not me, but
I will.